Welcome to our demo. We are NanoLogic for the VLSI Design Lab course sponsored by Apple, and we have designed a RISC-V-based SoC, as you can see here. So this is based on Open Hardware Group's CV32 E40P core, and it lacks the FPU that's a part of that core, but we support RISC-V 32-bit instructions of I, M, and C. So from there, also on the chip, we have 16 kilobytes of data memory, 16 kilobytes of instruction memory, and various peripherals. So on the peripherals, we use an AHB bus, and many of the peripherals are APB, so we have bridges for those. So we have GPIO, which is all set to inputs due to area constraints on the package. We could not do the in-out pins, so we stuck with input. So the GPIO is responsible for these 8 buttons. We have 8 of them, so 1 for each button. And then we also have UART. UART, as you can see through this adapter, this is an FTDI adapter. It takes UART to USB. So we have a configurable UART. You can change the baud rate and all of that. We also have configurable SPI. So that's what we're using to control the LCD. This is an Adafruit SPI to LCD backpack. It's responsible for controlling the LCD via SPI, so we don't have to have wires for each of these many pins. And then finally, we have 2 timers. The timers on the chip are just 32-bit timers that constantly wrap around, and we use them for various features such as randomization. So for the PCB itself, as you can see, we start with our Arduino. This is responsible for controlling the I/O for the scan chain. So the Arduino is 5 volts and our scan chain is 3.3 volts. So we have these voltage dividers here, one for each of the channels, and they're responsible for taking that 5 volts down to 3.3 volts so they can be fed into the chip. The Arduino has a program on it that just takes basically the binary data we send it to from the computer, and that programs it onto the chip. So moving a little further down, we have our power button. This controls 5 volts and 3.3 volts. You turn it off, and then you can turn it on, and then we have power. Moving over a little bit, we have our controls for clock and reset. So the internal clock has to be switched off when we're scanning in the scan chain, the same thing with the reset. So once we're done, we can turn the internal clock on and the reset on, and that will start our program. We also have down here, this is our chip, and a little further over, you can see all of the header for UART. Now, if we come over here, you'll see these 3 sections. These are responsible for taking that 5-volt power and converting it to about 1 volt for the chip. So you can see we have various capacitors here. These are all capacitors for decoupling noise. We noticed when we were testing on the breadboard that a lot of the scan chain noise especially would get into other components. So these are all to prevent that. We even have it on the 3.3 volts, as you can see up here. We also noticed that the chip is very particular because the clock generator is heavily voltage dependent, and because UART needs a specific baud rate. If the voltage is too high or low, UART won't work because we won't see it on the terminal. So these potentiometers allow us to dial in the voltage exactly. So we have VDD core, which is the core voltage, VDD test, which goes to our scan chain and test FSM, and then VDD clean, which is the input for the converters that go from 1 volt to 3.3 volts on the I/O. So from there, we have our SPI output to the backpack. This is backpack from Adafruit, as previously mentioned. The nice thing about this is it supports both I2C and SPI. We have the solder blob jumped for SPI. And then we have a contrast control, which controls the LCD. Adafruit provides an Arduino library for this, which we converted to use with our chip and its SPI registers and into our own custom driver. Moving down a bit more, you can see we have our buttons for GPIO. These buttons each are a Cherry MX red switch, and they basically are 2-pin switches, so they just connect together or don't. In order to control GPIO, what we do is we feed them 3.3 volts, but by default, it's pulled down by these 10K ohm resistors to ground. So when we press it, it gets pulled up to voltage, and we register a press. Finally, as you can see, we also have these various test jumpers over here. The test jumpers are just to help us adjust the voltages before letting them run into the chip. Otherwise, we may risk frying the chip. We also have the test outputs over here. This one is to test the clock internal. So we have a count out, which is a 1/1000th the speed of the internal clock gen, but it allows us to validate that that's working. So for our demo, we have preloaded the demo program onto the chip via the Arduino, and so to start, we enable the internal clock, and then we do reset. As you can see, we have a nice welcome screen, and then we have the menu. So our first option is print primes, which will print it over UART. Then we have play game, which is a reaction game. Then we have print pi, which prints pi over UART. So let's start with print UART. So for print prime, you can see we print the first primes up to 1000. So let's see that again. So there you can see that. And then next we have the other print UART, which is print pi. So we look at print pi, and you can see we're calculating pi, so the first 500 digits of pi. So that's all well and good. And so yeah, you can see it's pretty fast. So next we have the game. So the game is reaction game. It will tell you what letters you need to press. This is A, B, C, X, Y, Z. And then you have to press those letters. So we have 3 modes. We have easy, normal, hard. Let's start with easy. So we press start. So I have to press A. You see I press A, X. Very good. But then, oops, that's not an X. That's not a B. But what if I press Y? Oh, it's too slow. So it's timed and you can't press the wrong button. But let's see if I just press all the buttons at once. It knows I'm cheating. It won't let me do that. So that's good. And then I can get game over and return. So let's try normal mode. So as you saw previously, that was 1 letter at a time. So the 1 letter is responsible. The timer is randomization for that. So with normal mode, we have 2 letters, and since we have 2 timers, each timer controls the randomization of a single letter. So on normal mode, we press start. As you can see, we have 2 letters. Oops, that was wrong. That was correct. Oops, that was wrong and wrong. And then we get game over. So from there, we can go back to the main menu, and then we can try hard mode. So hard mode is very hard. We use the combination of the 2 timers to allow any letters and any combination of letters. So you can have 1 letter or all 6 letters and anything in between. So we press start, and you can see this is 5 letters. This is very hard. It's very, very hard. That guy got correct. Correct. Too slow. But yeah, you can see that mode is very hard. And so then you can press select to go back to your main menu. And that is our demo.